Steve has done a lot of the really seminal work in active learning over the past decade or so. So it's exciting to see what he has in store for us next.
Hey, thanks. It's been a great workshop. I've really enjoyed every talk. Okay, so I'm going to talk about just standard pool-based active learning, binary classification, and with label requests from a pool of unlabeled data. And we're really going to sort of get into the theory of, from sort of this classical like VC theory pack model kind of perspective. Most of this is, most of what I'm going to talk about is sort of buried in the proofs of this paper, and then there's a few follow-up papers. Some of them are on my website, and some of them are published, and others will be on my website sometime soon. Okay. Of course, the thing we're always contrasting with is passive learning, so I should define that first. We have a data source, a learning algorithm, and some expert. These are the players in this scenario. And what happens is we get some unlabeled data from this data source. The expert annotates the data and feeds it into the learning algorithm, which does some processing and then eventually outputs a classifier. And if all goes well, we hope that classifier should basically agree with what the expert would hypothetically say if we were to get new points from that data source. Of course, the idea then is the expert goes away and we just keep the classifier. In contrast, in active learning, all the players are the same, but now that unlabeled data is fed straight into the learning algorithm, and we let it choose its own which points should be labeled. Basically, it'll choose one, request the label of the data point. The expert then labels it according to whatever concept you're trying to learn. And then this happens again in several rounds. So it's a sequential interactive process. After a number of rounds, the learning algorithm eventually outputs a classifier. And again, we're hoping that classifier would agree with the expert hypothetically on future instances from this data source. So the motivation here is we would oftentimes sort of the wall clock time or effort bottleneck in a learning problem from the time when you decide I want a classifier till the time you have one is that you have to get a bunch of labeled samples. Oftentimes the unlabeled data is cheap, but this expert's time may be costly. And so we want to sort of maximize the amount of information we're squeezing out of this expert per amount of time or effort. Just by focusing on only the most informative or least redundant, given what we've already seen, samples. And so the key theoretical question is, how many label requests are required in order to obtain a certain accuracy? And this is called the label complexity. And we're most interested in when is this, or how much smaller is this compared to the analogous quantity for passive learning. This has been studied quite a lot over the past decade. Okay, so there are kind of two veins that one could follow in a talk like this. So one is active learning gives you a benefit of a more efficient search through the hypothesis class. And this is really the most studied way of discussing the benefits of active learning in a general VC theory perspective. And I'm actually not going to talk much about this, but if I was, I would be discussing things like disagreement-based versus margin-based versus splitting algorithms. And we would get into some interesting issues of, so you've all seen like the image of a binary search, and this is what we're talking about with that. I'm only going to talk in this talk very coarsely about this. As I said, there's a decade of research on this and a lot to be said, but I'll only talk about it at the very coarsest level that I can get away with. Because I want to focus almost entirely on the second benefit, which is only very recently we're really understanding how important this can be for obtaining optimal label complexities. And specifically, when I say active learning is beneficial for dealing with noise, I'm going to talk about heterogeneous noisiness. And this is heterogeneity is a theme that's come up in a few of the talks now, actually. And this heterogeneous noisiness, what I mean by this is some regions of the space are more noisy than other regions of the space. And active learning can help you sort of detect that and adapt to what regions are more noisy than others, and change how many queries you're making in each region. And this is actually something you have to do if you want to get the optimal label complexities.
I have a question.
Yeah.
What do you mean when you say noise? When you mean noise, you mean that the labeling is not deterministic, or you mean that you have some hypothesis class and you assume that things come from this hypothesis class plus some model of generating?
Yeah, so we'll actually define formal noise models in a bit, but to directly answer the question, in all of the noise models except for some things at the very end that I'm going to discuss here, it's just non-deterministic. So it's the probability that it's different from the Bayes optimal classifier. So it's the non-deterministic aspect. OK, but I have conjectures about the other case, and I think the same ideas will also give you optimal rates there. But OK, so the talk is basically in two parts. The first part is math and formulas and things of this sort. I'll be stating the definitions and the label complexity results themselves. And in the second part, I'll be talking about the algorithm. Some people will enjoy the first part better. Some people will enjoy the second part better. If you're in the latter category, don't despair. When we get to the second part, you can. It has very little dependence on the first part, I guess, is what I'm saying. So hopefully, though, everyone should be able to follow. And I want this to be as interactive as it needs to be. If I'm saying something that you don't understand and you want to understand, please interrupt and ask a question. OK, so in order to talk about label complexities, we should define a formal setting. Here, there's going to be a concept space, C. It's a set of binary classifiers that map an instance space, X, to a label space. It's binary classification, so we'll just take -1 and 1. We have a target distribution, and that's just a distribution over the instance space and label space. And we'll denote by eta the regression function, just the expected value of y given x. So that's a real value between -1 and 1. And the error rate of any classifier is just the probability it makes a mistake on a random xy pair from this pxy distribution. And we'll denote by f star the Bayes optimal classifier, which is the sign of the regression function. And as I mentioned, in the noise models that we will state results for in this talk, we'll always be assuming that the Bayes optimal classifier is in the concept space. It's not an assumption that we're happy with, but it's what the techniques that I'm going to describe work for, although I have conjectures about generalizing them beyond that.
Just a quick question. Yeah. So in cases where that's not true, is it generally the case that the additional amount you pay is at most the examples that fall into symmetric difference?
Can you repeat it?
The question.
I was wondering that in cases where this is not true, where the Bayes optimal classifier does not lie in the concept class, is it generally the case that the additional label complexity that you would potentially pay is at most the examples that would lie in the symmetric difference of the, like, do the schemes generally have that?
I don't see a reason that would be the case.
You can show that in deterministic cases, you get 1 over epsilon square label complexity, even if it's deterministic. Once the f star is not in C, then the rate can be 1 over epsilon square, even if it's completely deterministic.
OK, so you're not including the noise, the parameter about that Sanjay was talking about, the misfit between the model and the true target function. So if you include that, I think that you get a different bound. I'm saying if you include that parameter in the bound itself, I think you'll. Oh, I have a conjecture on the last slide. Okay, but yeah. I don't know why that would be always the case, but it could be. Yeah, I'm not sure.
So it could be a lot worse than that, potentially.
Yeah. Let's see. So it could be that, and then also the randomness would come into it. So right. So on the last slide, if you still have a question about this, come back in. So I do have a conjecture that it's related to this quantity, but also with the noise involved in it. So it's the overall error rate of the best classifier. Right. OK. OK, in the learning problem, right, there's a sequence of IID examples, XY pairs, from this distribution, but the labels YI are just hidden from the learning algorithm. And in the active learning protocol, we request them. Oh, they're hidden, or like they don't exist until we request them, however you want to think of it. So the algorithm chooses basically an index in the sequence, requests the label, and it receives the YI that corresponds to that XI. And then with that information in hand, it chooses another index. And this goes sequentially for up to n times, where n is a budget that's provided to the algorithm. Passive learning is just a special case of this that requests the first n labels or a random n labels. It doesn't do it sequentially, basically. I guess technically this is semi-supervised learning, but for our purposes, it's the same label complexity. OK. I'm just going to talk about label complexity in this talk. So I'm not going to talk at all, really, maybe toward the end a little, about how much unlabeled data you need in order to get these guarantees. I'll just assume we have as much unlabeled data as we need. It could potentially be a lot, but that's actually one place for potential improvement in these results. So just to define label complexity now, it's a kind of a pack style of definition. We say an active learning algorithm A achieves label complexity lambda, which takes epsilon, delta, and the distribution as arguments. If for any epsilon and delta, if you take the budget larger than lambda, then with high probability, 1 minus delta, the error rate that's achieved is at most the best possible error rate plus epsilon. OK. And we'll be studying a minimax label complexity. So this is, here we have some family of distributions we're interested in, and some family of algorithms. And then we take the worst label complexity among distributions for the best algorithm in the family. And we're just going to consider two families. So this is all, you don't have to parse all of this. Basically, I'm just introducing lambda A is the active learning minimax label complexity. Lambda P is the passive learning minimax label complexity. OK. And we'll instantiate the family of distributions as various noise models, basically.
Is the reduction, since you said that U, the number of samples can be very large?
Unlabeled, yeah.
The unlabeled data. Then it almost sounds like it's a membership query kind of problem.
Well, you couldn't query outside the support of the distribution, for instance.
Sorry?
So for instance, yeah, you couldn't query outside the support of the distribution.
Right. So, but your algorithm may depend on the distribution, so it knows the support. So you basically have a membership.
OK, the algorithms we're going to talk about don't know the distribution.
Because it's gamma. OK. So gamma depends on. OK. You see. So the algorithm does not know the support, but even though gamma does depend on it.
Yeah, this is just a description of what guarantee the algorithm achieves. It doesn't actually describe what the algorithm knows. Okay. I think it doesn't even matter for the results whether it knows it or not, though. So I don't know if that clarifies. But, OK, so are there any questions about any of these basic definitions of label complexity? Or feel free to hope not to lose anyone who wants to follow. OK, good. All right, so we'll talk about these, in order to state these label complexity results, we're going to talk about them in terms of two complexity measures. And these are distribution-free combinatorial complexity measures, just to keep things as simple as possible in the talk. One is very old, it's the VC dimension, and the other is relatively new, the star number. So the VC dimension, hopefully you've all seen in an intro machine learning class, right? It's just the largest integer such that there exists, the integer k such that there exists k points that you can classify in all 2 to the k possible ways using classifiers from your concept space. The more recent one is the star number. We denote it by s. It's the largest integer k such that there are k plus 1 classifiers in your concept space, h0 through hk, and k points, x1 through xk, such that hi disagrees with h0 only on xi among those points. Okay, so in other words, you can hold the labels of these k points fixed while flipping just one of the labels and hold the other k minus 1 of them fixed. And you can do that for any of the k points. You can hold the others fixed while flipping that one label. That's the star number. And so if there's no such largest one, we say the star number is infinite. Okay. So I'll just do a couple of examples. The talk isn't really about the star number. There's a lot of cool stuff that I could say about it. But if we're talking about threshold classifiers, so there's just it's a one-dimensional linear separator, basically, then the star number is 2 because like h0 could be between 2 points, and then you could flip one label while holding the other, or flip the other label while holding that one fixed. And you can convince yourself you can't do this with 3 points. In 2 dimensions already, linear separators has an infinite star number. So if you put some points on a circle, you could have an h0 that labels them all the same. And then for each one, you could have some separator that just separates that one from the others. So star number is often infinite. There's some decision stumps. It's like twice the dimension. There are some interesting cases where it's finite, but often infinite. So that's the basic definition of the star number. So as I've said, if I was giving a talk on the search through the hypothesis class benefit of active learning, I would be talking about various kinds of active learning algorithms and their relative benefits. And the thing is, if I really wanted to describe those relative benefits, I would need to introduce other complexity measures that have dependencies on the distribution and the target, and or possibly some data-dependent complexity measures. And a bunch of these have been proposed in the literature, and I've listed most of them here. And the cool thing that happens is actually in all of those cases, if you maximize them over the choice of the distribution or the data in the data-dependent one, so maximize over the choice of distribution or data set, you recover exactly the star number in every case, which is pretty cool because they were defined before the star number was defined. So we didn't plan it to happen, but it happens.
Yeah. These things change dramatically if you have extremely starters that positive example.
Well, I mean, you can, like for interval classifiers, that improves dramatically, but if you have 2 intervals, it doesn't improve dramatically, right? So yeah, you can always. Yeah. But those kinds of things have, there's some other work that looks at what if you can ask for examples from a given class, things like that. You definitely do get improvements from that compared to just asking for labels at chosen points. Yeah.
So when you say the worst case here, you are taking, I see, okay. Notice now you have a max over P in all of these things because.
Yes, max over the distribution, yeah. You hold the concept space fixed and maximize over the distribution, or the data set in case of version space compression, and empirical teaching dimension also maximizes over data set. Right. So this is also convenient in the proofs because I can use results that were proven for these various complexity measures to prove things about bounds in terms of the star number.
Do you think there's a distribution-dependent way of unifying them, though?
I think so, but yeah, I mean, look, if you want a really good complexity measure, the splitting index is awesome. There's some lower bounds that almost match the upper bounds. It's just a little log difference, but I think there's a little room for improvement over that, but not too much. Like there's a factor of VC dimension in question, but other than that, yeah. There was another question?
How is it related to VC dimension?
It's bigger than or equal to the VC dimension, but otherwise the gap could be infinite. Okay. Right, so those, with those complexity measures in hand, we can state some label complexity results. So just as a sort of a warm-up, let's talk about the simple setting of the realizable case. So realizable case here is defined as a family of all the distributions such that the optimal classifier is in the concept space and its error rate is 0. So this is like very unrealistic, but it's a nice toy model that allows us to build some intuition in some cases. So for passive learning, the minimax label complexity is known to be up to constants, VC dimension over epsilon, plus 1 over epsilon log 1 over delta. It's a fairly recent result. And for our purposes, we'll just say that's theta tilde d over epsilon. So we're going to sort of hide log factors to keep things clean on the slides. In active learning, the result is the minimax label complexity is roughly the minimum of the star number and d over epsilon. There's a small gap that you can prove you can't get rid of, but basically that's what it is. And the key here is that you get a better asymptotic dependence on epsilon if and only if the star number is finite. And again, if I was going to talk about the other benefit of active learning, search through the hypothesis class, I would then say, well, star number is often infinite, but let's not despair. We can replace it with these distribution-dependent complexity measures, and actually you can show you can always get some advantage over passive learning, at least in an asymptotic sense. But that's sort of an orthogonal direction from here on in the talk because I want to talk about benefits that you can get from noise. So I'm just going to stick with the star number as the coarsest possible description of that other benefit to keep things simple. So just to get into that issue of noise, still kind of in a warm-up mode, here this is a noise model that we'll call benign noise. So it's a set of distributions such that the optimal classifier is in the concept space, and the error rate of the optimal classifier is at most some value nu, which we call the noise rate. Okay, so the sample complexity of, or label complexity of passive learning in this setting is known to be the noise rate over epsilon squared times the VC dimension plus the realizable case, basically. And that's an old result from Vapnik and Chervonenkis. And the new result here is that it's in active learning, the optimal label complexity is basically the noise rate squared over epsilon squared times the VC dimension plus the realizable case active learning label complexity. So the improvement over passive is that we have multiplied this term by another factor of the noise rate. A few of you who have studied the theory of active learning in some detail may be thinking, oh, there's a typo on this slide. There should be another factor here, some complexity measure like the disagreement coefficient. But no, this is actually, you can just have this, which matches the term in the lower bound, essentially. And you have to use the techniques that I'll be talking about in the second half of the talk in order to get that kind of benefit. Any questions so far? So, so that was a noise model, but I mentioned we're going to mainly get our benefits here from heterogeneity of the noise, and a really great noise model for describing distributions that have heterogeneous noise is this Cibikov noise condition. This is like what it's designed for, to characterize those distributions. So this is Cibikov noise. It has two parameters, A and alpha. Alpha is really the important one. it's a set of distributions such that the optimal classifier is in the concept space. And for any epsilon, the probability that you get a point whose regression function has magnitude less than epsilon is like epsilon to power depending on alpha. So here, large alpha gives you a better noise condition. It's like lower noise, and small alpha is higher noise. So this is saying the probability, so eta near 0 is a very noisy point, and eta far from 0 is a not very noisy point. So just to sort of draw a picture of what this is, if we had like threshold classifiers on the line and say a uniform distribution on some segment, maybe the regression function sort of looks like a sigmoid or something. It sort of smoothly crosses the 0. Here's where it would flip from, the optimal label would flip from -1 to 1. And if that's a very sharp transition, that corresponds to an alpha that's up near 1. And if it's sort of a very flat transition, then that corresponds to an alpha that's down near 0. So you can see the probability of the noisy region, the very noisy region, would be larger if it was flat, and it's small if it's sharp, like in the picture. Okay.
Well, and what would the benign noise look like here?
A benign noise can kind of do whatever it wants as long as the optimal classifier doesn't have too large of an error rate. So it can be a threshold plus like some patches, as long as everything to this side is negative and to this side is positive. It can sort of do whatever it wants as long as the area adds up to the right number, the noise rate.
So it's basically no assumption, or it is?
Well, it just all has to add up to the noise rate, and also to the left has to be negative and to the right has to be positive. Or 0.
No, but if you make Sivakov, then you can, in terms of Sivakov, relate what nu should be, right?
Okay, yeah. So if you take a limit as alpha goes to 0, then the sort of the A parameter is going to this rate.
Sivakov is stronger than benign noise because it's assuming some form of the noise as opposed to yours, which could be any kind of shape just as long as it's total area.
It's not assuming a form, actually. This is just for a picture. This is just for a picture. But yeah, I mean, this is anything that satisfies this condition. It just happens that sort of the worst case distributions put a lot of noise near a separator often, but that only comes out in the analysis. There's really a lot of distributions here that look crazier than this. Okay, great. So that's Sivakov noise, right? And the behavior at 0 determines alpha because of how it transitions. That's just in the picture again, but yes. Okay, so this has been studied a lot in passive learning, and the optimal label complexity is known to be like A times the VC dimension over epsilon to the 2 minus alpha. So as alpha goes from 0 to 1, this transitions between that 1 over epsilon squared kind of behavior to like a 1 over epsilon kind of behavior. If you remember, the realizable case had a 1 over epsilon times VC dimension. So this alpha parameter sort of lets you interpolate between those two extremes. And right, so that's passive learning. And in active learning, I'm going to state the result in 2 parts. The first part is sort of the high noise case, where alpha is between 0 and 1/2. And we get a very simple result there. Active learning gets a squared VC dimension over epsilon to the 2 minus 2 alpha. Okay, so what we did is we took passive learning and multiplied it by a epsilon to the alpha, or improved by a factor of 1 over epsilon to the alpha, however you want to say it. And just to, if you sort of blur out everything else and just look at the epsilons, what we did is we took an epsilon to the alpha minus 2 and made it an epsilon to the 2 alpha minus 2. So it's an improvement by multiplied by epsilon to the alpha. So again, in the literature, you often see a bound that looks like this times another complexity measure. And this new technique allows you to just get rid of that and get a tight bound. So that was the sort of high noise case, and this is the low noise case with alpha between 1/2 and 1. It gets a little more involved in that case, where we get sort of a gap between our lower bound and upper bound. You could actually prove you can't get rid of that gap. But I've written it in a sort of funny way so you can compare the terms in the upper and lower bound. But you can simplify that upper bound to just be a min between something that looks like what we had on the other slide, but times a term that's depends on the star number. And then we have another term here, which is just VC dimension over epsilon. So if you sort of strip everything else away again and just look at the epsilons, well, we've really nailed down the dependence on epsilon. If the star number is finite, you get 1 over epsilon to the 2 minus 2 alpha, which is what we had on the previous slide also. So again, that's improving by multiply that by epsilon to the alpha. If star number is infinite, you get a 1 over epsilon, which is also what you get in the realizable case if the star number is infinite. So we're basically, again, getting something like a max between the strong improvement and the realizable case. And it's always, both of these are smaller than passive, right? So passive, this is always bigger than 1 over epsilon. So even when the star number is infinite, it's still smaller than passive. And again, we have to use these new techniques in order to get this. Okay. Are there any questions about any of the, that was the end of the label complexity section. Next comes the algorithm, but it's a good time to answer any remaining questions about label complexity.
I mean, you said you're not going to talk about it, but do you know something about the case where F star is not in C?
The last slide, yeah, you have to wait. Okay. Great. So next is the algorithm. So I apologize if anyone got lost in the first part. Come back to us now. We're going to have pictures. It's going to be great. Okay. So the algorithm that achieves all this magic is the following. It has a kind of a general outline to it. You have something called getSeed, which is basically an active learning algorithm, like another active learning algorithm, but usually just something designed for the realizable case. You have a subroutine which we call TicToc. It's an acronym I'll introduce later, which sort of handles all the queries. And then at the end, we have some way to pick a classifier to output. We call that learn. That could be a passive learning algorithm or something like that. OK, so mostly we're going to focus on the new part. But just in order to describe how this algorithm functions, I better define for you an algorithm for the realizable case. And for that, we'll just actually pick the simplest algorithm for the realizable case for active learning. This is a disagreement-based approach due to Kahn, Atlas, and Ladner. We call it CAL from their initials. And just for illustration purposes, I'll describe it in terms of linear separators. But you should keep in mind that everything I'm saying holds for general arbitrary concept spaces. So the way this algorithm works, I'm just going to define it by pictures, basically. We have our pool of unlabeled data, and we're just going to sort of draw points at random, and for each one, decide whether or not to query it. And the beginning's a little boring, so I'll fast forward. Let's say that we've queried all these points so far, and then the next point we draw from the pool is this one. Now something cool happens because all of the separators, the linear separators in this case, all the separators that label these as minus and these as plus, they all agree this has to be plus. So in the realizable case, if you remember, they're all consistent with the optimal classifier. So we can actually just infer that this label should be plus. We don't even have to query it. We can just color it ourselves or throw it away. It actually doesn't matter for this. And then continue. Draw another sample from the pool. Let's say next one we get is this one. OK, now it's not so easy because there is a separator that is consistent with all the labels we've seen, labels it plus, and another one consistent with everything we've seen, labels it minus. So there is some disagreement about what this label should be. And so this is the algorithm queries it. And this is sort of the definition of this CAL active learning algorithm. If there's some disagreement, we go ahead and query. And if you think about the set of all points such that there is some separator consistent with the data that labels it plus and another one consistent with the data that labels it minus, those points sort of form a region colored like this. And we call this the region of disagreement. And so cal is defined by the property that it queries a point if and only if it's in the region of disagreement, and draws them at random and queries them if they're in the region of disagreement. Of course, after you query the point, then you sort of implicitly are able to update the region of disagreement. And so this continues. You can infer some labels. Maybe you get another point in the region of disagreement. You query it, update. Another one, query it, update. So you can see over time it's sort of shrinking. I should say this is a nice picture for presentation purposes. Sometimes it's not shrinking so quickly. OK, so if the region of disagreement happens to be shrinking, the algorithm then queries less frequently, and that corresponds to an improvement over passive learning. OK. All right. At the end, you can just output any separator consistent with the data. So that's cal. That's designed for the realizable case. Of course, if you had noise and you query a point, you can't trust that that's really the optimal label. You don't just want to update. So you have to modify this algorithm in some way, or it'll do crazy things when there's noise. So if we want to make it noise robust, so we want to make it noise robust, and that's where we're starting to move toward that TicToc subroutine that's going to basically make realizable case active learning algorithms noise robust. Here's the first attempt. So the idea would be, let's say, well, here's our unlabeled data. Let's say cal happens to query this point. What we might do is take a bunch of samples nearby, let's say its nearest neighbors, and run a sequential hypothesis test. Basically, we're trying to figure out, based on the labels that we're seeing, whether this region is dominantly labeled plus or minus. And there's some really great, I saw Akshay around yesterday, I don't know if he's still here, but there's some really great hypothesis tests based on the law of the iterated logarithm. There's a finite sample version of that works really well for this. And then you can decide eventually whether this is a dominantly plus region or minus. It looks plus in this case. And then you would just go ahead and infer you'd go ahead and label that seed point according to that inferred label, update, and continue. This works great if you have a regression function that is bounded away from 0. We call that bounded noise. But you can show that under Tsibikov noise, it uses too many labels. Basically, it'll spend the vast majority of its queries on a very small number of very noisy points. And so it's just not going to work well for, it's not going to get those optimal label complexities. So in particular, it takes roughly 1 over the square of the regression function number of queries in order to determine the optimal label at a given point.
Steve?
Yeah.
So maybe I don't get the intuition about looking at the nearest neighbors, because you're not making any a priori smoothness assumptions on the regression function, right?
That's right, yeah. So I haven't, I've sort of hidden some thing that I'm doing here. Not an assumption, but an actual part of the algorithm. There's a metric. And it's really tricky to define it for arbitrary VC classes in arbitrary scenarios, but you can do it. And we can talk afterward. It's not nice to state, but I can, yeah. And that's another place for improvement. Maybe there's a way to clean up and make a nicer metric to use in this. But yes, that notion of distance is very carefully chosen so that this works.
I see, and that sort of involves the hypothesis class and everything. Yeah.
Yeah, it involves the hypothesis class. You even use some unlabeled data when you're defining it.
Okay, so it's distribution.
Well, it's data dependent, yeah. So modulo that detail, where you have to define a metric using the hypothesis class and the unlabeled data in a very careful way, but it can be done. Right, so that doesn't work. That basic idea of just do a sequential hypothesis test, figure out what the optimal label is, and draw another point and continue. That doesn't work, but so in sort of figuring out why it doesn't work, one insight you might have is, well, it's spending a lot of time querying very noisy points. Maybe we want to focus instead on the less noisy points. And there's sort of 2 really good reasons for doing this. One is we actually care more about less noisy points. So if a point is very noisy, the regression function is very close to 0. getting the label wrong, meaning like not classifying it according to the optimal classifier, doesn't really even hurt you that much. Like if it's a 0.49, 0.51 probabilities, if you guess the wrong label, you only get a 0.02 increase in your error rate for that location, whereas some other place where it's a 0.1 versus 0.9 probabilities, well, if you guess the wrong label, that's a 0.8 difference. That's a big deal. So you really care more about the less noisy points. And then there's sort of a double bonus on top of that. It happens that this and this coincide. The second benefit being that it takes fewer queries to determine the optimal label on the less noisy points. So we're in a sort of lucky that the points we actually care about also take the least number of queries to determine what the optimal label is there. Right, so that's if the regression function is very far from 0, this is a small number. So we can sort of combine those two ideas, or those two motivations, and design an algorithm that sort of adaptively figures out where the less noisy points are and focuses more on those. OK, so the algorithm is going to kind of start by operating the same as before. So we're running this realizable case algorithm, and that's your get seed. So it picks a point, let's say this one. And now we're going to invoke this TicToc subroutine. So this is tiered cutoff in a test for the optimal classification with surrogate points. OK, so that has the convenient acronym of TicToc. And what we do is the same as before. We were running a sequential hypothesis test. We're querying points that are very close by and trying to determine what the optimal label that dominates this region is. And but the change here is that we're going to have a cutoff. So if we have exhausted Q queries and still haven't figured out with this test, still haven't figured out what the optimal label is, we're just going to give up and we move on. So we actually just throw that point away and pretend it never happened and draw another point. Let's say this one. And now let's say we do our sequential hypothesis test. And this time, before we've reached Q queries, we were able, with this sequential hypothesis test, to figure out what the dominant label in that region is. And we go ahead and infer, in this case, it was red. So we go ahead and infer that label for that point and do the update to the active learning algorithm, in this case to the region of disagreement, and we continue. And then at the end, you just output a separator that's consistent with all the samples that we were actually able to infer the labels for. And then we sort of want to gradually decrease that value of Q over time so that we end up focusing on more and more, or on less and less noisy points as the algorithm runs. And that's what shifts the distribution or the samples toward the querying mostly on less noisy points. This is the algorithm that achieves that label complexity bound that I stated earlier. And as I said, you can keep in mind this actually works for arbitrary concept spaces, even though I showed it just for linear separators. OK. Were there any questions about the algorithm?
Also, one thing you might do is sort of be smart about the next point you want to.
Yeah. So that's that's from that sort of other benefit, the search through the hypothesis class. There, you're sort of very carefully picking points to search more efficiently. It turns out it doesn't make any difference in our bounds because we were using distribution-free bounds where like the star number is in there. But if you did want bounds that have dependence on the distribution, you would be using other distribution-dependent complexity measures. Then in order to get the best bounds there, you would have to be more careful in how you pick. Here, we can just be kind of lazy because it turns out you can still get the optimal bounds for that.
I missed how did you decrease Q of SM?
Yeah, it does. I just said it. I can tell you what it is.
You just said you gradually decrease.
I just said you gradually decrease. I didn't tell you what the value is.
Why is it? What's the intuition for not starting small?
Well, you could start small and increase too. All that matters is that in the end, the proportion of each amount of noisiness is the right in the right amounts in the data. You're actually, let's see if there, that's the value of Q. As the sample index increases, it goes down like 1 over the sample index squared. And it has some other factors. That's a bonus slide, all right. I'm not actually going to go through the proof, though. You can feel free to talk offline.
It's very nearest neighbor in spirit, this algorithm.
The query mechanism is definitely nearest neighbor in spirit. Of course, at the end, we're outputting a separator. And the sample, the querying is sort of nearest neighbor. You're querying in local neighborhoods, but the choice of which seed point is, that has to do with the concept space that you're working with. Yeah. So the particular algorithm I showed here. Yeah. So you're outputting something from the version space, basically.
So this is a denoising procedure combined with a.
Yeah. Right. It's a way to denoise the queries of a realizable case active learning algorithm. Okay. I do have some results for other settings that was all for VC classes, and you can look at larger classes under distribution assumptions, just like in passive learning. So this is one that's been studied. If you have a smooth regression function in addition to Tsibikov noise, and you have something called the strong density assumption, like your densities away from 0 in a compact regular sport. Passive learning gets something like this, and active learning again improves by multiplying by epsilon to the alpha using this TicToc idea, along with, and this one does use a nearest neighbor kind of strategy, a lot like what Sivan talked about earlier. And then combines that with this TicToc idea. I've also been playing around with some probabilistic Lipschitz settings, and you can kind of also use these ideas in those settings too. Right, okay, this is that slide that I've been promising all along. Open problems. Reducing the number of unlabeled samples. So it can be very large for some distributions. I think there are actually distributions. I'm still working out the details of it, but I think you can get by with a polynomial number of unlabeled samples if you have linear separators in a very nice, like uniform distribution or something like that. The computation is an issue, even in addition to, so a lot of the computational burden here is just dealing with how much unlabeled data you need. So if you had some nice data structure to handle that, this would actually be fairly efficient. Also the metric can, which I didn't define, but that can be a little expensive to evaluate. But okay, so here's the thing I was promising. I have a conjecture that these benefits can also be realized even when the optimal classifier is not in the concept space. So here, if we denote by nu c, the error rate of the best classifier in the concept space with no other assumptions, I think you can get that with active learning, the error rate of the best the error rate of the classifier that you can find is the most the error rate of the best in-class classifier plus epsilon, using at most this many queries. So this is actually the same bound that I showed for the benign noise setting earlier. It's the noise rate squared over epsilon squared times the VC dimension. So Sanjoy, this would include the model misspecification error and also the probability of mislabeling just due to randomness. This would match a lower bound. So this is a known lower bound proven by Sanjoy and friends, and Lena and John, I think, were on the iWall paper. And then this is just the lower bound from the realizable case. I guess modulo whether this should be a plus or a times. But so that would be basically optimal if it's true. I have some reasons for thinking it's true, which I could discuss with anybody who's interested. But I don't know how to make these techniques work in the general case to get this result. But I think it can be done. Okay, and I think that's it.
Any more questions?
So I was just wondering about one high-level intuition issue with the algorithm. So it could happen that initially whenever my query budget in the test is higher, I still happen to draw a point that's sort of less noisy, so I didn't anyways need that many queries. And then when I did get a point that is more noisy, my query budget has gone down by that point, so I never end up seeing any representative data in the noisy regions of the space. So is it just that the quantities are set in the right way so that the Sibakov assumption kind of makes sure that the probability with which you're going to see a noisy point is small enough, or what's the intuition?
Yeah, it's set very carefully to make all these things balance. I guess that's maybe the answer. Yeah. So if it happens that I'm decreasing this cutoff so fast that I miss an entire class of noisy points, because of the choice of how I'm decreasing it, that must be, with high probability, a set of points that I didn't care about anyway, that they were so noisy that we could just ignore them. So there is actually epsilon to the 1 minus alpha. So if your regression function is smaller than epsilon to the 1 minus alpha, you can just ignore, what I'm saying is accurate. You can just ignore them entirely.
So just to understand, your algorithm is kind of like a nearest neighbor denoising followed by regular learning?
Yeah, it's nearest neighbor denoising in addition to just realizable case learning, but with this trick of there's a cutoff in the denoiser where I can just give up if it's too expensive, and I decrease that over time.
Do you see any maybe advantage of using that kind of approach even in a non-active setting? I mean, you could try some, would that have some reason kind of cool?
Yes. In fact, there's some literature on like nearest neighbor methods that are compression based, where they sort of compress a neighborhood down to a single point, and then they just use one nearest neighbor with those individual points that sort of represent a whole region of the space.
Right. But they're just using nearest neighbor. Here you have a combination of like nearest neighbor denoising followed by some other learning approach.
Yeah, maybe that you could use this in to help out with a log or something. I mean, we have optimal passive learning for VC classes with Sibakov noise, but there's a log maybe that can help with that. Yeah. Log in the upper bound that's not in the lower bound. I don't know.
So is this a secret metric of yours easy to describe, say, for linear separators or something?
Sorry, is it what?
So you said you have a hard to describe metric in which you do everything, right? And if I say take a nice class like linear separators or something, is it easy to describe?
Yeah, I mean, like I mentioned that I'm still working on details, but I think there's an efficient thing for linear separators that are nice distributions. That's just using Euclidean distance.
I see.
Yeah. I mean, I think a lot I can just use whatever the ambient.
I didn't mean for computational efficiency, just even for intuition. I was curious what the metric might look like in that case.
Okay, I mean, I can just tell you the metric. It's not nice, but you just take some unlabeled data, you look at all the possible ways that you can separate it, and then like a point here is as far from a point there as the number of separators that disagree on the two. That's the metric. Actually, Rob has used this in other work also. Okay.
Having distance of the dual class, kind of.
Yeah, Hamming distance in the dual class for some unlabeled data inducing it. Yeah.